In our video on adding vectors, we'll start off with a simple case first up. If we've got two vectors, one in pink moving to the left and a green one moving to the right, which has got a greater magnitude as we can see here, you'd expect the resultant to be a vector moving towards the right-hand side. But this is a simple case. How do we show it when the vectors aren't necessarily opposite to each other? How do we work out a resultant vector? So a good strategy to do would be to first of all identify some key parts of the vectors. And we can talk about the tip and the tail of the vectors. The tip is where the arrow is, and the tail, if you like, is the end of the vector. That's easy to remember if you think of the arrow as leading the way. So what we do to add the vectors is we arbitrarily identify one vector as the first vector and the other vector as the second vector. And what we're going to do is join these vectors such that they join tip to tail. We do this by leaving the first vector as is, and we take the second vector so its tail joins the tip or the arrowhead of the first vector. The resultant vector shares the tail with the first vector and goes towards the tip of the second vector. So we can see that here in this diagram. There's the tail of the first vector, and this becomes the tail of the resultant vector, and the tip of the second vector is the tip or arrowhead of the new resultant vector. Let's have a look at another case now where the vectors are not parallel. In this case, we'll call our green vector the first vector again. So what we're going to do is take the tip of the first vector, the green one, and match it to the tail of the pink vector. And it's easier to see here the end resulting vector because we've got the black dot which represents the tail of the first vector, and we've got the tip or the arrowhead of the second vector. Altogether, this gives the resultant vector in black. And it does make sense because we've got two vectors both moving towards the right, so the resultant vector should have a greater magnitude towards the right. We've got the green vector moving horizontally and the pink one moving slightly northwards or up, and so the black vector should be in between those two directions. Let's now take this concept of vector addition into an example. It would be wise to pause here and have a read for the question yourself and see if you can isolate the key information. So what we know from this question is without any effect of the wind, we've got a plane that can fly at 400 kilometers per hour. The first part of the question is asking us about a direction the plane must fly. So what's mostly critical at the moment is that we know that it wants to fly at a bearing of 55 degrees. We'll use the distance of 800 kilometers later when we need to determine how long the journey will actually take. We also have a wind speed of 70 kilometers per hour from a bearing of 110 degrees, which will affect the direction that the plane needs to take. So the most critical part of this problem is actually setting up a diagram so we can perform our calculations. So let's have a look at a sketch, and it is a sketch. The first time we might make some errors and we might need to make a neater diagram at the end of what we've done. The first thing we'll do is draw a line which represents the resultant vector, in other words the path we want the plane to take. That's an 800 kilometer journey. And what we'll then need to do is put vectors that add up to that resultant vector. Let's draw some further lines and we'll put some angles in a moment, but keep in mind that's at a bearing of 55 degrees. Now our two vectors that are going to add to that resultant are the plane and the wind. So we'll put the plane vector as the first one and the wind as the second one. So the arrow for the wind is going to finish at the end of that blue line. So that's the 70 kilometers per hour. And note it's coming from a bearing of 110 degrees. We'll show that more precisely in a minute. We also now will place in the vector for a plane. Now that vector is going to start at the resultant's beginning, in other words where the tail is, and then the arrow will join up at the tail of the wind vector. So we'll place that in now. And we can see here that the wind is going to affect the journey of the plane such that it pushes it to the resultant vector in blue. We need to determine the direction of that green arrow. So let's start putting some angle measurements into our diagram. The easiest way to do this is to draw the compass bearings at each of our vertices, in other words north, south, east and west. And we can use this to create parallel lines and therefore angles within parallel lines. So we know the bearing of the resultant journey of the plane is 55 degrees. And that will have an alternate angle in the top right hand corner that we've just drawn there because north-south forms a parallel line. The wind is coming from 110 degrees. So we'll draw a line that has a bearing of 110 degrees, but you can see that the brown arrow representing the wind is coming from that direction. We can see here with the north, south, east, west directions that that'll create a 20-degree angle. And vertically opposite that is another 20-degree angle. Of course, alternate to that is another 20-degree angle, and to the left of that will be a 70-degree angle because it's the angle between south and east to make 90 degrees. So now we can find the angle at the top of our triangle by adding 55 and 70 degrees. And that gives us an angle of 125 degrees at the top vertex. So putting all this information together, we need to ask ourselves what we're trying to do. And of course, we're trying to find the direction the plane needs to take to satisfy this resultant journey. In other words, what's the bearing of that green vector? At this point, before we go any further, it would be wise to make sure our diagram was neat and the information was clear. So when we put our diagram together in a neat format, we can see that what we want is the angle in the bottom left-hand corner of the triangle. We want that because it will help us give a bearing of the 400 kilometers per hour vector. So that means that we have one angle, we need another one. And we've got two sides in terms of the velocities. We're going to ignore the 800 kilometers for a moment because that represents a distance as opposed to a velocity. So we need to keep the units the same. So just repeating that, we have two velocities and we have two angles. Admittedly, one of them we don't know. We need to find a bearing. So that would suggest we're going to use the sine rule. And what we need to now do is identify the sides with respect to the sine rule. We've got an angle, A, of 125 degrees, and opposite that is a velocity of 400. We've got an angle we don't know in the bottom left-hand corner, and opposite that is a velocity of 70. Now, some calculators will solve for angle B very quickly at this point, but what we can also do is multiply the opposite side to sine B by 70 and solve that on a calculator. When we do that, we get an angle of 8.24 degrees. Now, using the sine rule, we should always check for a second angle and then ask ourselves if it makes sense in the context of the triangle and the practical problem. In this case, the other angle would be 180 minus 8.24 degrees. Let's say it's approximately 172. Well, that isn't going to fit in the triangle we can see with the 125 degree angle, so we can ignore that. So our bearing is 55 plus 8.24 degrees, which comes to 63.24 degrees. What we now want is the time taken for this journey. So what we need is the resultant velocity shown here with the letter C. We know the displacement or distance for the journey is 800 kilometers. We'll assume the velocity is constant. So what we need to do is work out that velocity and then put it into the formula for velocity, displacement and time. So we can see in this diagram we have got two velocities. We want to find the velocity where the lowercase c is shown, and we have got one angle. So in effect we've got three sides, admittedly one of them we don't know, and one angle. So that means we're going to use the cosine rule. The key thing to note for the cosine rule is where's the angle and what's the opposite side. So angle A is 125 degrees and lowercase a is 400 because that's the side opposite. B and C represent the sides that are adjacent to the angle, and we've already identified C as the unknown velocity. So B is 70. And we can substitute those values into the formula. Most calculators that are programmable should be able to solve that quickly. So the value of C that we get is 355.72 and the units are kilometers per hour. Now what we need to do is answer the question, which is ask how long will the time be to take that journey. Whilst we are talking velocity vectors here, the formula that we're going to use is the same because we're assuming a constant speed. So the time taken is the distance covered divided by the speed. We know the distance covered in the original question was 800 kilometers, and we have a velocity, or in this case applying it as a speed, of 355.72. When we do that calculation, we get 2.25 hours. Now this time can be converted to the nearest minute by taking the decimal amount of hours, in other words 0.25, and multiplying that by 60. And the time becomes 2 hours and 15 minutes.